for different temporal sampling. Here it's in the case of monosensor datasets, and what you can see is that we have here in red the classical temporal inversion, in green the Chiku methods, and in orange the moving average. To do that for each time step, for example, of 20 days, if the temporal sampling is of 20 days, we average all velocities which are overlapping this given temporal sampling. And we can see on this graph that the root mean square error is way better with graph, that the root mean square error is way better has stabilization 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 mean square error
One
velocity, which is not visible in the simple velocities based on optical data. We can also see that there are discrepancies between processing chains, so here's the processing chain from each line, and we have values which are close to 0, which are not visible in the other datasets, such as here with the Soutenance datasets. So the challenge here is that we have simple velocities from different processing chains, but not necessarily in agreement. Etienne, tu nous entends toujours? Okay, so we propose a method which is first to average all simple velocities on the cursor grid. So here it corresponds to the grid with a 200 per 200 meter resolution, a spatial sampling. And then to apply Tickle without prior weights. Then to here the most important improvement in the methodology concern the computational time, because we have larger data sets, so it's become very important. So we use LSMA, which is a solver optimized for sparse matrices, matrix where you have a lot of zero. And we still carry on an iterative weighted least square. And then we use the residual foundation to analyze our result. Il y a un problème. Okay, so here are still the north-south velocity components, and here you have the result of the fusion using all simple velocities available. And what you can see is that here we are seeing the velocity variation, and if you look at the residual, indeed there's no bigger residual for simple velocities based on optical data. So a possibility is when here on this period of time there are a lot of clouds over the area. So it's possible that the moving average is impacted by the simple velocities, which have a first and last dates, which are before and after this period of time. So that gives the impression that the velocity variation is smoothed. The other thing which is interesting is here, if we look at the residual of the inversion over this area here, so on the top of the western tributary, we can see that the east-live simple velocities based on optical images are larger than the other one. And if we remove it from only the upper parts of the glacier, then here on this area is the result of the fusion, but using all the dataset except its line, we tend to have smoother results with less noise. And the last thing which is very interesting is when you look at east-west velocity component of the velocity. So we use the same type of fusion. And here you can see that in the upper part of the western tributary, we tend to see a velocity variation, a seasonal variation, but it's very difficult to highlight. Where here with the fusion, we can see that there is peak of velocity here. I'm going to show you better with a larger figure and a different color. And what is very interesting is that if you look at here the bottom part of the glacier, you can see that there is maximum of velocity around May, which occur later on the upper part of the glacier. And that corresponds to an increase in temperature, which leads to a different subglacial hydrology, which occurs sooner on the lower part of the glacier than on the upper part of the glacier. And this kind of analysis was not possible before to carry on the fusion. As a percent conclusion, we have shown that simple velocities based on different processing chains are not necessarily in agreement. To fuse them have the interest to increase the number of available velocity observations in the system and find a consensus between different types of information. it's still a work in progress, and we will need to carry on a systematic analysis of the residuals and improve our way to analyze the uncertainty of the results. And as a general conclusion of this presentation, I've shown that we have a very high amount of sim pair velocities available, but still underexploited. And to show you a conclusion, you remember the video I've shown you in the introduction. It was very difficult to analyze these data sets. With the fusion, we have a very easier way to analyze velocity variation. We provide velocity time series with a reduced uncertainty. The mean square error is reduced by up to 17%, a regular and temporal sampling, a better and spatial coverage, and a data volume reduction. Here, the dataset over this part of the glacier has a volume of about 25 megabytes, whereas with all the same pair velocities, it was about 250 megabytes. So we divided it by 10. And so during this PhD, I also have been very lucky to collaborate with other colleagues on different subjects which are related with the fusion parts. First, on the estimation. So as I told you, we tried optical flow method, but we also carry on the first analysis of the generalization of a convolutional neural network. And we also work on the SAR co-registration using one ground control point. For the analysis parts, we studied time series clustering by comparing PCA approach and autoencoder approach. And that draw a global view, which can be used to draw some perspectives. First, on the methodological perspectives. So over a short term, it would be to automatize the hyperparameters of flow methods to be applicable over a larger scale. We can also carry on fusion of optic and SAR sim pair velocities, but in the SAR geometry. It's something I've worked a bit in the end of the PhD, and I've shown some results in the manuscript, but we will still need to work on that to then retrieve 3D velocities, which can be compared with changes in surface elevation. We can go also on a longer term to the fusion of a global dataset of velocities. Here it was only based on image correlation, but it can be also computed using INSAR or GPS measurements. And here are some papers which can be interesting to go in this direction. We can also use the fusion results as a training datasets for especially multi-frame convolutional neural network. Here's a paper which can be interesting. And for the glaciological perspective, over a short term, it can be to fuse all available sim pair velocities of ice velocities over a larger scale, such as some region of high mountain Asia, and over a longer term to carry on clustering and data mining methods, to carry on also joint analysis with other variables, such as topography or the melting onset derived from SAR images. And this particular point will be the purpose of a postdoc funded by the CNES and starting in March at the IGE in Grenoble. Thank you to my three supervisors and all my co-authors, and thank you for your attention.
Thank you, Lauranne. I think unless there are some specific reason, maybe we can switch to French for